Welcome back, everyone. Determine the hybridization and give the bond angles around the highlighted carbon atoms for the species given below. We're given two structures. We can begin with the first one. And what we want to do is just expand the bonds. First of all, we're given a methyl group, CH3, that is bonded to the carbon of interest. That specific carbon has two hydrogens bonded to it, as well as an unpaired electron, so it's a radical. Our first step is to always determine the steric number. How many bonds and lone pairs of electrons do we have? Well, we have 3 bonds and no lone pairs. So the steric number is 3. We can completely neglect the unpaired electron. We are only worried about the presence of lone pairs, and a single unpaired electron is not a lone pair, right? So we only have 3 carbon, hydrogen, and carbon-carbon bonds in total, right? So the steric number is 3. And we have to recall that a steric number of 3 represents an sp2 hybridization, which corresponds to the trigonal planar geometry. Trigonal planar geometry has an ideal angle of 120 degrees. In this case, we can say that the observed angles would be close to the ideal angle because we don't have any lone pairs of electrons. What about the second structure? We once again have a methyl group that is bonded to carbon. That specific carbon has 2 carbon-hydrogen bonds and a negative charge. What does it mean? Well, essentially it means that such a carbon has a lone pair of electrons. According to the formal charge formula, if we take 4 minus 3 bonds minus 2 lone pair electrons, that gives us the negative charge on carbon. What is the steric number? Well, in this case, we have 3 bonds plus 1 lone pair. And now it gives us a steric number of 4. A steric number of 4 gives a hybridization of sp3, s1p3, 1 plus 3 equals 4. We can use that trick. And now sp3 hybridization is consistent with tetrahedral electronic geometry. But what about the actual geometry? Due to the presence of that lone pair, we can say that this geometry would be trigonal pyramidal. Okay, and now generally the ideal bond angle would be 109.5 degrees for a tetrahedral geometry, but if it's trigonal pyramidal, due to the presence of a lone pair of electrons, the bond angle would be reduced by about 1.5 degrees. Generally, this geometry is consistent with the geometry around nitrogen and ammonia, and we can expect an angle of 107.3 degrees. Remember that each lone pair of electrons decreases the angle by actually about 2 degrees, right? If we have a 109.5 degrees as an ideal tetrahedral angle, we essentially subtract 2 or 2.5, right? Between 2 degrees and 2.5 degrees for every lone pair present. So we would then have about 107 degrees for ammonia with 1 lone pair. And a famous example would be water. We subtract 2.5 degrees and we get around 104.5 degrees for 2 lone pairs when it comes to tetrahedral electronic geometry. In this case, the experimental angle is about 107.3 degrees. And that would be it. Let's label our answers. For the first part, hybridization would be sp2, and the bond angle would be about 120 degrees. For the second example, hybridization would be sp3, and the bond angle would be around 107.3 degrees, it's perfectly fine to use a 107, right? Because we can just approximate it. And that would be it. Thank you for watching.